Right. Good morning, everybody, and thank you very much for that, Faith. When you say I'm hugely experienced, that just means I'm getting older. What I'm going to do this morning is introduce you to what we do within CROSS and within SCOSS. We'll then show some examples of failures and some examples of near misses and how we handle those. We'll then touch on Grenfell and matters beyond that, the Hackitt report and the Hansford report, and then we'll talk about what we as engineers can do in order to make the process safer for ourselves, which is very important, but also, most important of all, for the public. Now, can you all see the slides at the back? Is the lighting okay? Right, we have three sponsors, and the sponsors are the people who provide us with funds and who guide what we do, and principal amongst those is this institution. They've always been very keen on safety, and they've been always very keen on what we do. Second are the Institution of Civil Engineers, who are coming more into prominence post-Grenfell because of infrastructure concerns. And then, of course, HSE, which is absolutely fundamental to safety in general, and they are the third leg of our sponsor. So we've got a very stable kind of three-legged stool. And that is the group. A minute, I've got the hang of this. Underneath that comes structural safety, which is just a name, but the two bodies which really count are SCOSS and CROSS. Now, SCOSS is the Standing Committee on Structural Safety. It's been going for over 40 years, and it was started because of various disasters which had taken place, including the Ronan Point, a building which collapsed due to a small explosion, and bridges which failed as well. So SCOSS was brought into existence in order to collect data from public sources, because at that time, of course, there weren't internets, there wasn't immediate access to all sorts of information, so you had to wait until something was publicised and perhaps until something was published. I see lots of you are taking notes. I believe these slides will be available. Oh, is Jane here? Yeah. So they will be available on a website somewhere, so you'll be able to pick up from there if you want. SCOSS then considered, is there an unacceptable risk? And their duty at that time was to report it to the President of the Institution of Structural Engineers and the President of the Institution of Civil Engineers. And then, if it was decided there was a risk, that an alert was published, and that went round industry. Now, we still do that, and that's still important. And here are some of the recent alerts that we've published. This one on the right we'll come to again, but that was fire in multi-storey car parks, when there was a huge fire in a Liverpool car park, destroyed 1,300 vehicles. A very important issue, and we'll come to why later. Then there was a steel frame which collapsed in London. This was a building which was ready to be completed. It had been topped out, and minutes after 40 people left the site, it came down and collapsed totally. So it was a near miss for 40 people. However, the building was intended to be for religious purposes, and the ground floor was going to be a hall, a congregation area where up to 1,000 people could have gathered. So it was possibly a near miss for something like that. And in order to create this big space at the bottom, they wanted to have no columns, so there was a huge girder at the top spanning right across, and the other floors were hanging from it. The reasons it collapsed are not entirely certain because the exact trigger wasn't found, but there were a lot of construction defects, a lot of issues, and that is given in our alert, which was published in February last year. And then there was the business of the Edinburgh schools, where a number of schools were found to have issues. It all started off with this school here. I'm trying to get a red button and I can't seem to.
It's just below the two arrows. There's a red.
Oh yeah, right, thank you very much. A high wind one morning sucked out a panel of 9 tons of brickwork, which fell on a path where those two guys in the high-vis things are. And had it been a few hours later, that would have been full of primary school children and their parents. So it was a near miss for them. The defects which were discovered were found to be endemic and covered a lot of schools. And you will find the details of that in the SCOSS alert. So we publish stuff very relevantly, and even in this day and age, when a highly regulated country, a highly regulated engineering community, we still get issues like this. So there's a little bit more about the City Gates building, photographed taken just after the topping out ceremony, and that's what it looked like afterwards. So a catastrophic sudden collapse. And here are a couple of the reasons for it. One, if you imagine this being upside down, on that there should have been a hanger welded, but obviously the welding didn't take at all, so the hanger just fell off. This is part of a tensioned connection, and so there was a piece of steel coming down, another one coming up. The two should have married up, and bolts should have gone through the holes. They didn't marry up at all, so more holes were drilled in order to make it work. So you had what was in effect the edge of a postage stamp, which just sheared. So these are issues related to the fabrication of the steelwork. So what we do is we try and learn lessons from these things. And there are various lessons here. For example, a local failure shouldn't cause a disproportionate collapse, which is an inherent part of robustness. Hangers are something which don't have much ductility. And if you're trying to avoid sudden collapse, you want to have as much ductility in your system as possible. You want it to kind of yield a bit. It can sag, but it shouldn't fall down. And this is a key point in earthquake engineering. And connections, of course, are vitally important. And you should worry, for example, about welding vital connections on site. And you should obviously not amend a connector, such as drilling extra holes, until you've talked it through with the designer. I'm sure none of you do those things, but it did happen. And the contractor should always be aware of the risks of an unusual structure. So if you've got something which is not run-of-the-mill, and the contractor must be made aware, and everybody concerned, that this is a structure which has got special requirements. So we now move to what does CROSS do, and Faith was very instrumental in this a few years ago, in deciding that there were lots and lots of events which happened, but which never got reported. They weren't published for various reasons, and yet lessons could be learned from them if we could find a way of gathering that information and learning from it and disseminating it. Now here is the process that we use, and we copied a lot of this from NASA, because 40 odd years ago there were a lot of aviation crashes in America. Pilots would come down and say, well, I had a near miss there, and the first thing their employer would do was say, okay, you're fired. So the Federal Aviation Authority, who were in charge of all this, decided that they needed a confidential reporting system, a no-blame system. And in fact, in America, if you're in the aviation business and you report something and it's not criminal, you will never be prosecuted for that. So that's a kind of get-out-of-jail-free card. We don't have that here. But we do and have always worked with, alongside NASA, to make sure that our processes and theirs are the same. So a report is received. It only comes to me and our senior engineer called Paul McNulty. We're the only ones who ever see a report. And we've both got very bad memories, so after a while we never realise who it's come from. Because although we need a name in the report, we don't actually use that name ever. We simply may want to phone somebody or email them and check a few details, but in due course, that name is shredded from our system. The report is then processed to produce an anonymised technical issue which doesn't mention sites or products or names of contractors or clients. That's then given to a team we've got of a dozen or so experts who are real experts to say, what can we learn from this? Now, how many of you get cross newsletters? A goodly number, that's great. So the comments which you see in the cross newsletters are a distillation of what's produced by our expert panel. We will then take that report and the comments back to the reporter and say, this is what we're supposed to publish. Are you okay with that? Inevitably, they say yes. We then pass them through a lawyer because we want to make sure that no comeback can affect the reporter or indeed ourselves. So only when all those steps have been taken to be published, we publish the stuff on the internet. If it's an important one, we will put it in newsletter, and if it's very important, and particularly if we've got a trend, then we will put those in a SCOSS alert. So that's our publication. And then the most important part of the whole thing is the answer to the question, well, so what? So we try and influence affairs, and I'll show you one or two examples of these, but we try and get something done. If we found a concern, how can that concern be addressed by those in industry? It might be in future guidance, it might be in a change in regulation, it might be in a British standard or whatever. So that's the goal, is to complete this virtuous circle. Now, quite familiar product in terms of risk is a risk pyramid. Now, this one is adapted for the aviation industry. There are similar ones in financial circles, in medical circles. You know, a surgeon will have a risk pyramid when they are deciding whether or not they're going to do something dire to your insides. At the bottom, in our case, there are the normal functions of what go in design offices, what happens on sites. Then you get an incident where there may be a concern, but nothing has actually happened. Then you'll get injuries, and finally you get fatalities. Now, nobody's going to come to us with the fatalities. They're going to go to the police, they might go to HSE or whatever, but there will be a body well above our grade which looks at that. So CROSS is interested in everything up to the bottom of the red line. SCOSS is interested in the more serious things, including the red line, but of course we won't get stuff on that until after an inquiry has taken place and something is published. And all the stuff down the side here are precursors. So if you can pick up a precursor and you can pay attention to it, then you may be able to avoid the following up of that by a disaster of some kind. So here are the sort of things that we get. Now that diagram on the right is a small segment of a finite element analysis of an exceedingly large building, multi-story. The green elements are vertical load bearers, the red elements are horizontal transfer slabs or beams. And if you take that through a whole mass of a building, it all looks absolutely splendid, it's all in colour, but the concern is, do people actually know what they're modelling? Is that model a real representation of the structure? And even if it is, do the people know what they're analysing? And this particular reporter's concern was, what about progressive collapse? Where is the robustness in this system? He says, I don't know where the loads are going. And we get quite a lot of stuff about computer systems. And are they accurate replicas of what we mean to build? The one on the bottom left is a tower crane which collapsed, and it was a tower crane with a luffing jib which had a 50-ton counterweight on the top. It fell over backwards. The 50-ton weight went through 6 floors of a building without hitting anybody. And the reason it failed was at the base, where the tower crane system landed on a pile cap. There was obviously heavy connection required between the two, and yet there was a clash between some holding down bolts from the tower crane and some heavy bars coming up from the pile through the pile cap. So the designer and the site organizer decided between themselves, without real reference to anything, to cut off a number of the bars from the pile cap and epoxy in a few bars instead. These obviously had no strength, it failed. There was an HSE prosecution in that case, and the parties were found to be guilty. And this one is, on the right, is a Ronan Point type building. Now, all of you are far too young to remember much about Ronan Point, but this was where a system building consisting of floor slabs and wall panels, which were kind of piled up together and connected in a not terribly good way, initially, solved the housing crisis in the 1950s, early 1960s, because you could put these up quite quickly, living would be good in them, and they were structurally thought to be fine. Nobody thought about robustness, nobody thought about progressive collapse until Ronan Point. Now, this is one which was demolished a few years ago because it was not required anymore. And it was known to be consist of panels which were all meant to have been strengthened after Ronan Point. All these old buildings were looked at, connections were refreshed, strengthened. So this had been through that process. But it was still thought that possibly it might be vulnerable. So the client told the demolition contractor, be very careful about this, we don't know quite what's there. So a demolition contractor got up a crane beside it here with a concrete nibbler on the top, nudged the top corner, and the whole lot came down. So there was another progressive collapse. And large panel structures are in the news at the moment again. They're being looked at post-Grenfell. So what sort of causes do we get? We analyse our reports and we give them a primary cause. Now this is, in a sense, simplistic because all failures have multiple causes. But there's usually a prime cause. And we consider that in the pre-construction stage, about 36% are related to issues to do with the design. The blue sector are issues to do with construction, which are roughly the same. And then the green sector are events which happen during the normal life of a building or a bridge. And there's not so many of those, but we think that's because not so many engineers are involved in the life cycle of a building. Once the construction is complete, they generally go out. So there are probably more failures in the green sector, but we don't record those. We then analyse what happens, for example, in the design stage, and we find the biggest sector that is inadequate design principles. So people who are either not aware or not have thought of fundamental principles. And then there are other issues to do with inadequate design and inadequate checking and communication and so forth. We then, during construction, we can divide that up. And the biggest sectors are the two on the right, and they are inadequate competency and inadequate site supervision. So the human factor there accounts for 50% of all the issues which happen on site that get reported to us. And I stress this again because this is not necessarily a complete picture. It is what we see. So here is an example of looking at precursors. And these are anchor failures. Now, about 15% of our reports are to do with anchors and fixings. They are often neglected. The designer will say, connect X to Y, and it's left to somebody much further down the chain to decide, well, we'll buy a fixing, and often somebody will, doing a bit of value engineering, will say, well, there's a cheaper fixing available down the road, get that one. Now, the picture there on the right is of a ceiling which collapsed, and I always look up at heavy ceilings. Now, this was in a cinema for heavy acoustic insulation. It was 50 or 60 mil of plasterboard. There were speakers, there were lights with various bits of gear up there. And yet the fixings, which have failed, these skinny bits of wire, were the kind of thing that you would put a very light suspended ceiling up with. So no thought was given to what is going to hold that ceiling up. No casualties, fortunately. This is an example. You can see all these bolts going in at skewed angles. These were bolts holding angles. The angles were holding up the precast stairs in a multi-storey block of apartments. Putting the bolts in meant that they had to avoid the rebar, but they couldn't avoid the rebar. They put the bolts in any old how. And the result was like that. So again, it was a near miss, because nothing happened. But here are some examples of failures where chemical anchors have caused near catastrophes. The one at Balcombe Tunnel, the Victorian Tunnel, there's some steelwork above, which is part of the electrification system. So it's ancient brickwork, but still trains go through there on the way from London to Brighton at 100 miles an hour. And you can't really see it, but that steel platform is sagging because the bolts holding it up, which were into the masonry, have fallen out. They've been falling out for years. Inspectors have been going along, looking at the tracks and kicking these things and saying, oh, there's another bolt. I wonder where that came from, and never looking up. So that was a near miss. One which wasn't a near miss was Boston, where heavy ceiling panels connected by epoxy bolts to the tunnel roof collapsed. There were fatalities, and that became known as the $1 anchor, which caused the $1 billion claim. Huge problem. And then in Japan, very, very similar thing, the Sagasso Tunnel, where there were concrete components forming a flat roof and air ducts above them. That collapsed because the bolts were inadequate. They had never been inspected. They'd never been checked. In that case, the collapsing panels caused a fire, and quite a number of deaths followed. So a simple thing like a fixing. And if you can find the precursors, you may be able to do something. So here's what we were able to do. We published an alert back in 2010 about these things. We published guidance along with the Construction Fixing Association, which is the trade body looking at fixings generally. British Standard Code of Practice was changed using our material. Then this year, Syria have published new guidance, and the Bridge Owners Forum have published new guidance for all the fixings related to major bridges. So our virtual circle has been completed. Here's another issue which is relatively common, balcony failures. That is a building with balconies at 2 levels. The higher level balcony has just fallen on the lower level, been there for 40 years, and the rebar was found to be in the bottom of the slab, not in the top. So people have been walking on this quite happily as a cantilever which was completely unsound. Photograph in the middle I can't show you because for legal reasons, but it's a very similar case in France recently where 6 people were killed when a balcony fell down due to the rebar in the wrong face. And then this is one in Berkeley, California. That's timber which sticks out, and there was a party being held on a balcony at a student residence, and that came down, and 6 students were killed in that. So just simple balconies can create problems. So what are we doing here? We've had 21 reports, which is a significant-ish number. We're preparing a report. There is a committee, British Standard Committee, looking at balconies now, so that has been submitted to them as evidence, and we'll see what happens. Temporary stages. The one over here is a small stage for a small event, and it's got a roof which is fairly simple, but it's got some mass to it. It's got some very heavy speakers in the corners. So in earthquake terms, it's an inverted pendulum. All the mass is at the top, and all that's holding it up are scaffold tube at each corner. So the reporter who sent that in said, well, I'm a bit worried about this. What's holding it together? The one on the right came from another reporter at about the same time, but coincidence. And that was somebody who had been checking a temporary stage at a site for a concert and found that the corners of the top of the stage were connected to the ground by strops, and at the ground were large water tanks. So the idea was these water tanks would act as kentlage, and if there was any swaying of the temporary stage, then these water tanks would stop it. But their concern was, well, water's not very good. What if somebody just opens the tap, for example? So those are precursors. And then here's something which actually happened. And a few seconds after that, a number of people were killed. And you can see the similarity. All the mass is at the top. All the windage is at the top. The vertical elements are very spindly. The wind which caused this is not very high because you can see ordinary tents here unaffected. And these corners were held by guys, and down here there were concrete weights. But the concrete weights in many cases were on grass. And as this thing started to sway, the weights just slid along the grass. So I wouldn't imagine people in Indiana would be reading SCOSS Alerts from earlier, or SCOSS reports. If they had, somebody might have thought more deeply about this. So what are the outcomes from temporary stages? We published an alert. That alert was used in the London Olympics, where there were more temporary seats than permanent seats. So all of those were checked in accordance with the principles that we had proposed. And finally, guidance from the institution has been updated in 2017 on the procurement, design and use of temporary stands. So again, we have completed our virtuous circle. So here are the benefits of confidential reporting. First of all, Eleanor Roosevelt said, learn from your mistakes, because you can't live long enough to make them all yourself. But the system identifies safety trends, and that's very important. 1 report is good, 2 reports is great, half a dozen reports shows there's a real trend, like the balconies, 21 reports on that, or 100 reports on fixings or whatever. They illustrate an important trend. It's a proven system. It's been proven by the aviation sector, and we've been using it for 13 years, very satisfactorily. It promotes a blame-free culture, and this is important because lots of inquiries into why something got wrong say, well, let's find the scapegoat. Like, who's responsible for this? And that's part of the culture of blame, isn't it, in the country? If something happens to somebody, you say, well, there must be somebody to blame. We don't do that. We're purely interested in promoting the technical lessons which can come out of it. It's independent, although we've got our sponsors, the sponsors themselves don't tell us what we can say in our reports or alerts. And we act in the interests of you as well, because there is nothing, absolutely nothing in your career which is worse than getting involved in a fatality on a site or in relation to a building. It destroys people's lives, it destroys firms, it is an awful business to get into. And you would worry what letter is going to come through the post next, what court am I going to be called, or whatever. So it is really worthwhile avoiding and making sure you never get into a situation where you might be involved in any way. And also helps the industry, because of course companies which have been involved in bad events, they often go bust. Certainly can affect their reputation hugely. And then ultimately we want to protect the public, because that's, as our engineers, that's one of the requirements, that's one of the ethical considerations of what we must do. And then this is very important for you, we always need reports. This is the oxygen of our system. We don't get reports, we can't function. So you will all have had events which you might be able to report. You can just go onto our website, Structural Safety. There is a form there, and you can send the reports in, and they will be dealt with in the way in which you've seen. So please think about that, and I will look forward to a spike in reports coming in the next few days. It's very serious. Right, so how do we learn from failures? Of course, that's one of the things that this seminar is about. And it's education at all levels. So ultimately, learning means education. Now, you'll get information condensed by others, and that will include codes, guidance, institution publications, and the like. So somebody else has looked at all the things that have gone wrong and have incorporated those into advice which you can read. It's obviously easy now to Google something and see what you get from that, but be very, very aware of fake news. And if you should ever be called upon to go into a court and give evidence as a witness in relation to something, and you said, well, my lord, I got it off the internet, that will not go down very well. It's not regarded as a secure source for information. So it's very useful, it's very interesting, but don't just trust it on its own. You can follow what we do, and that will give you information on a fair number of safety issues. And look for patterns. Pattern recognition is critical. And pattern recognition is what, at this stage, artificial intelligence is about. Not really intelligent, it's looking for patterns and things. So if you see a pattern, then that can be a warning of something, a pattern of things going wrong. But it's something that we think AI will become very good at in the future. And AI related to BIM is another sector for the next generation, probably for people like you. And then keep repeating the reminders, keep telling people, keep giving talks, keep pushing the lesson through. So let's move on now to tragedies in tower blocks in London. And it's absolutely awful, isn't it, that in major cities, one of the world's major cities, we should have had 2 tower block tragedies. We've talked about Ronan Point. It's up there somewhere, which the minor explosion took place. There was mains gas in the building. A lady was going to make a cup of tea. There was a fault, an electrical fault. There was a minor explosion which blew out a wall panel. The wall panel then allowed the floor panel above to collapse, and so on. So that was a progressive collapse. And then, of course, there's Grenfell, absolutely shocking event. Now, we can't talk in much detail about Grenfell, but I can give you some information because it's under a legal procedure at the moment, and a judge is looking at all the issues. But there are certain things we can draw parallels to between Ronan Point and Grenfell. Lots and lots of issues. In both cases, change has resulted or will result. So Ronan Point changed the way in which engineers worldwide dealt with robustness. And things are much better connected now than they were. And you can knock out a floor panel or a wall panel, see a local failure, and you will not get a progressive collapse. Unless, of course, you're in that steel frame in London we were looking at. Grenfell will change our attitude to risk, and it will change our attitude to regulations. And in both cases, the designers, the constructors, the managers, and the ownership have all been involved in some way with what has happened. So, what did the government do? Well, they set up this inquiry under the judge, and that is taking place, and it's absolutely harrowing to see some of the stuff. And I was at a meeting yesterday in the House of Commons when the MP for Grenfell was talking to us about what has happened and the awful stories that come out of it. And she looked at us, and we were a bunch of kind of, older white people. And she said, what have you got in common with the fatalities at Grenfell and the survivors? But that's what we are. At the moment, we're the sort of people who are trying to resolve those issues. And then they set up an independent inquiry under Dame Judith Hackitt, who is very well respected within the industry, and she has led a team to look at what is the future for regulation and what is the future for fire safety following on from the Grenfell Tower. So we were involved with that, and we'll come to that in a moment. But let's look at precursors for cladding. Because cladding, of course, is one of the primary issues under the investigation at Grenfell. But it's not the only issue, and more you will see more. But there was a cladding fire in Australia, and there's one in Dubai. So those are precursors. But people said here, well, this can't happen. Our cladding systems will comply with the building regulations, so we couldn't possibly get anything like that. Now, that is what the Grenfell Tower fire looked at when it was first photographed at 1 o'clock in the morning. That was 15 minutes later. That was 20 minutes later. And you can see how the spread of the flame just engulfed the building within 20 minutes, half an hour at the most. Now here's a section of what the Grenfell Tower cladding looked like. So there's the original concrete. Been there since the 1960s. Fine, good, robust in situ concrete. And the robustness was important because despite that horrendous fire, the concrete by and large withstood it. But in order to insulate it, some foam insulation was bolted on the outside, and then finally an ACP cladding panel was put on that, and that's two very, very thin layers of aluminium and a layer of plastic in between. So the plastic on the outer layer is very combustible. This plastic is combustible. So the calorific value that was found of that composition is the equivalent of the calorific value of diesel. So imagine putting a thick layer of diesel around a building and saying, well, that's going to be okay. Now, the BRE and the government department did some tests. This is a pretty standard test, whereby you build a section of wall panelling and a re-entrant curve. There is an opening down here, and that simulates a window or a door, and inside is a crib of timber with a known calorific value. So that, if you set that on a light, you'll get a known fire strength capacity. Now that was with the Grenfell type cladding. The fire was stopped after 395 seconds because it was totally out of control. It had to be put out with liquid nitrogen. And you will see that the crib down here is hardly even blackened. So it got on fire, it had set up the cladding, and there was a total failure in terms of the British standard. Here is one which was done with non-combustible rock wool foam insulation and an ACM panel, same thickness as before, same aluminium, but a fire-resistant inner plastic membrane. And you will see here that the crib has been completely consumed. So that has passed a test. After 1 hour, there is some damage there, sure, but it's not catastrophic and could be contained. So that's one catastrophic fire. Here's one which didn't result in life loss, but easily could have done. And this is a Liverpool car park. And this is a Liverpool arena. This is its car park. And there was an event taking place on the 31st of December. In here, it was a horse show. So the arena was just filling up. The car park was full. There and there are apartment buildings. The one at the right is only 5 meters away from the car park. And down here, there is a high-class hotel. So the car park was in the middle of residential areas. A car on the 3rd floor caught fire. This is all on CCTV. The fire brigade were called quite quickly, but by the time they got there, the fire had spread to adjoining vehicles. It then spread so quickly within the building that it couldn't be controlled. And going back to our site here, this is a dock. And only by bringing in 3 very, very high capacity pumps and putting them under the dock was enough water obtained in order to prevent that fire spreading to the other buildings. The mains in the street were totally inadequate. So if the fire brigade had to rely on those, then the fire would undoubtedly have spread to the apartment buildings and possibly to the arena as well. Now, people got out of that, and here's a plan of the building. There were fireproof cores in the corners, and it's a usual array of parking spaces and ramps. Cars were abandoned on the ramps. People fled from them. They got out through the fire doors into these escape stairs and away. And you'll have seen stuff about fire doors at Grenfell which performed exceedingly poorly. These fire doors performed tremendously. There was this inferno inside, but the fire doors afterwards, the inner layers were completely charred, the outer layers were fine, so it did a terrific job. And that's what it looked like afterwards. So absolute devastation. But you see the in-situ concrete is spalled. It's still there, however. This is another view. We were able to secure the services of a drone company, and they had produced a device which came from Switzerland called an Elios, collision-tolerant drone. And this was great because it's surrounded by a carbon fibre cage, and we were able to photograph inside the building using this. The insurance companies later on went in with traditional drones, and they've lost 2 of them so far. So here's a lesson from fires, perhaps, and this is not usually talked about at all, but is there a calorific fire load in your building? Is it necessary to consider that? The calorific fuel load in Liverpool was the equivalent to a full tanker full of fuel. And as I say, at Grenfell, it's equivalent to coating the building with diesel. So high calorific value. Are the means of escape secure? Is there enough water? Can smoke and heat get through barriers? And is the structure robust? All questions which we have all thought about probably in the past, but have been brought to light by these big fires. And we don't want to see another one. Another guy I was talking to yesterday was an extremely important fire chief, and he said he dreads waking up every morning and seeing on the news that there has been another big fire somewhere. So, what did we do in terms of the Hackitt review? Well, we submitted evidence that we said buildings must be safe by design, safe to build, and safe through their lives. And Judith Hackitt's recommendations are for stronger and tougher regulations, a new joint competent authority. This is for what are termed HRRBs, high-rise residential buildings, but it may spread to all buildings. The joint competent authority is the Health and Safety Executive, local building control, and fire services. There's got to be a safety case approach, we'll come to that in a minute, that there should be further cross-reporting, and that there should be clear responsibilities at every stage. So safety cases mean, in terms of Hackitt, that there are a lot of gateways before you get to a problem, and then there are a lot of things to consider in mitigation should that problem occur. A slightly different safety case approach, and this is something you may get involved with more in the future, is to start a process by saying, are there hazards and failure modes and possible consequences? So that's where you think about things laterally. You look for problems and you identify them and you think as widely as you can. Then you prioritize those by significant, what are actually likely to happen. You eliminate those by good engineering, which is, of course, part of a CDM process as well. Are they as low as reasonably possible? And then, when you're actually on site, you want to confirm all the things that you thought were going right. If you thought that something was fire resistant, is it? Do you have a certificate to prove it? And is that certificate valid? If you thought your concrete was of the right strength, do you have the test certificates to prove it? And so forth. And then you look at the lifetime asset care, and that's the bit which probably was being missed a lot of the time. As designers, we often stop at that stage. Well, the designs are there, built, finished, handed over, and we pay no attention. But we should be thinking about the lifetime care of that structure, of that bridge. Then at the same time, the Institution of Civil Engineers got Professor Peter Hansford to review the infrastructure risk. And he found that whilst the risk of a major failure is low, it's not low enough. So what did he recommend? Very similar process, lines of defence for risk management. He too has recommended that our work should be built upon by the industry, that we should learn more from near misses. CPD regimes are going to be overhauled, both in this institution and in civils, and that we should all work together on lifetime safety. It's very similar to what Dame Judith Hackitt said, but she was talking specifically about tall buildings. Hansford is talking about big bridges, railway lines, and the like. And there's their Swiss cheese model, which is similar to lines of defence. You say, we've got lots and lots of holes in everything we do, whether it's a concept design, a detailed design, the drawings, the construction, or whatever. And you hope that you've got enough lines of defence that when you've got a hole, beg your pardon, when you've got a hole, it doesn't line up and it bounces off. But when you do get the holes going right through your lines of defence, that is when you can get a failure. And here is a reminder, a very timely reminder of this deadly bridge collapse in Italy, probably caused by a failure of those two ties, which were unconventional. And the Highways Agency here have been looking very carefully to see whether or not we've got any bridges of a similar type. And they've concluded that we haven't, but nevertheless a very close watching brief is being kept on what's going to come out of that. And that will be the subject of a SCOSS report in due course when it is published. So, what are the likely consequences? And one of them is that there will be changes to the building regulations, that there's going to be more rigorous processes, including these safety cases. Everybody is going to be competent, more competent, and Judith Hackitt produced the idea of a golden thread. Now, this isn't golden and it's not a thread, but she said you've got to take the client at one end, you've got to go through the design process, you've got to go through the construction process, you've got to go through the observation on site process, you've got to go through the handover, and so on, and you come right back to the client. And only when all those are connected together and kept connected together have you got a really robust system. Because it's systems that she's talking about, not the detail, but the whole system which is flawed and needs to be revised. So think about the golden thread all the time. Pass on what you know to somebody else and make sure that what people before you have discovered is passed down to you. And of course another thing at the very bottom of that is digital records of everything. It's going to be boom time for BIM. So, what's the likely impact on our profession? And it's those things, the things we've talked about. Greater awareness of risks, safety critical things, more competency, and more engagement probably in site processes. There's been far too much of forgetting what resident engineers do and not looking carefully enough at what is actually being built. Is that what the designer thinks is being built? And in the cases like Edinburgh, like the other collapses, it's not. So, coming to the end now, what you should be doing is some reflective thinking. And reflective thinking is looking at known risks and unknown risks. There was an American Secretary of State who was very famous in a war scenario talking about the known knowns, the known unknowns, and the unknown unknowns. And what you're looking for in real risks, you're looking for the unknowns unknowns. What might happen that is just kind of on the fringes of our imagination. Consider unexpected consequences. A small bolt failing on a bridge handrail may result in something falling onto a railway line and hence precipitating a derailment and a catastrophe. Happens. Be very wary of new materials, new forms of construction and emerging technologies. They will all work, but you don't necessarily want to believe them all at first. Want to be wary. Look at ageing infrastructure, because almost all our infrastructure is ageing in this country, and look for new methods of evaluation and repairs, things like drone surveys, things like repairing with carbon fibre, things like intelligent bridges, if such things can exist. And release safety critical information. So if you know of something, report it to us or some other means. Make sure that other people know about it so the lessons can be learned. And finally, we have got an international version of CROSS coming up. Faith was in Australia a couple of weeks ago and launched it in there. We are working on CROSS in America and Germany and Southern Africa and in due course other countries. And we hope to have a network of CROSS systems across the world with a common data hub into which everybody will put their reports and their advice so that people throughout the world, and particularly in developing countries, have got a resource to go to find out things that might help them avoid collapses and problems elsewhere. And finally, to a guy called John Smeaton, who was the father of civil engineering. Before that, all engineers were military engineers. He was the first man who called himself a civil engineer. And way back in 1770 odd, this is what he said, that you can sort out stone and wood and iron, you can fix them, that's the hardware. But the greatest work is to keep right the animal part, that's us, of the machinery. So thank you very much.